title of this section is Logical Equivalence and De Morgan's Laws. Now, before we get into logical equivalence and De Morgan's Laws, we're actually going to look in particular at conditional statements. And some variations. Conditional statements and variations of conditional statements. So remember, a conditional statement is the if-then, so P implies Q. Now, one of the biggest things to remember is that P implies Q is not the same as Q implies P. These statements are not logically equivalent, which we're going to officially define what logically equivalent means in this section, so we'll do that later officially. So we're going to define this officially, what it means for these to not be logically equivalent. But for now, let's talk about an example, or let me just give you an example. If I drink a cup of coffee, then I will not be tired. Okay, this statement, if I drink a cup of coffee, then I will not be tired, is not making the same claim as if I am not tired, then I must have, let's make this grammatically correct, then I must have drank a cup of coffee. So it's not necessarily about whether or not these statements are true, because we know there's different possibilities for there's different combinations of these two simple statements being true or false that give different combination or different outputs of true or false for each of these statements individually. It's what I'm not really making a note of that necessarily. I'm saying that these two statements they're just different statements. They're not saying the same thing. They're not saying the same thing. So we have to distinguish between these two statements and make sure we understand that these are not the same statements. And I'm making a big point of this because with conjunctions and disjunctions, so the ands and the ors, those are the same. If I said P and Q, that would be the same as Q and P. So those you can think of them as commuting, like in addition or multiplication, right? In addition and multiplication, you can flip the order and it doesn't matter. But conditionals are like, you could think of them like subtraction, right? They can't commute, they can't swap orders because you'll get different answers. They're different statements. Okay, so let's talk about some variations of conditional statements. So what if I was trying to get across this point, if I was trying to kind of combine these statements and I was trying to say, if I drink a cup of coffee, then I will not be tired, but I'm also trying to get across the point that if I'm awake, if I'm not tired, then I must have drank a cup of coffee that morning. Like I'm trying to tell someone I cannot function in the morning without coffee. Like let's say I'm trying to say it, but with an if-then statement. The way you would say that is, and no one really talks like this, but in math, this is how we say theorems that work in both directions. It's an if-then statement that actually does work in both directions. This is how we say it. I'll use this one. Or no. Let's say. I want to make sure it's grammatically correct. That's why I'm pausing. Yeah, it's going to make more sense if I use this first. I am not tired if and only if I have drank a cup of coffee. Okay, so no one really talks like this in the real world, in just normal conversation. But this phrase, if and only if, is actually really, really important. And it says that this is the only way that I cannot be tired, is if I drink a cup of coffee. And in fact, it says the other way too, if I drink a cup of coffee, I am not tired, but also, if I am not tired, I have drank a cup of coffee, right? So we combine both of those statements by saying if and only if. This happens only if this happens, and this happens only if this happens. It's a much stronger statement than either of these by themselves. We call this a biconditional, so it's a variation of a conditional, biconditional, and we denote it by, I'll put a colon here, P implies Q like that, except we put another arrow like that. So now it says if P then Q and if Q then P. So I actually just gave something away there. I just said that this is the same as saying if P then Q and if Q then P. So we can just make a note here and just say, since I kind of gave it away, this biconditional is logically equivalent, and we'll show this later, to, it's logically equivalent to P implies Q and Q implies P. Okay. But before we do that, let's look at a truth table for this biconditional, which really, we could just build a truth table based off of this because we know how to do this, and then the truth tables would be the same because these are logically equivalent, which is exactly what that means. But let's pretend like we don't know that yet. Let's just look at the table, and let's just try to, instead of using any rules about previously built compound statements and such things, let's just try to reason our way through the truth table for this biconditional. Let's see if we can figure out when this statement is true. So I say, let's see, what am I saying? I am not tired if and only if I have drank a cup of coffee. If both parts of this statement are true, then the whole statement is true. So you're seeing me holding a empty cup of coffee, and I look awake, so you see that both of these statements have been satisfied. I am not tired, therefore I have drank a cup of coffee, and vice versa, I have drank a cup of coffee, so I'm not tired. They're both satisfied. Now what about this statement, or rather this combination, true, false? So you see me and I look awake, but I have not had any coffee that morning. Then this statement, which essentially says I can only function if I have coffee, this statement would be a lie because I'm awake but I have not drank coffee, right? Because the second statement is false here. So here, just in case you didn't figure it out, P is I am not tired, and Q is I have drank a cup of coffee. Okay. So what about this second statement where the first part is false, so I look very tired. It says the first part is I am not tired, but it's false, so I look very tired, but I have drank a cup of coffee. But I told you this statement, which implies, or which really says that I can only function if I have coffee, and vice versa. So you see me drinking a cup of coffee, but I'm still tired. That means this statement is false. And now we get to the weird one where both parts are false. So we get to this weird, like, it's kind of like that case in the conditional where it's actually going to be vacuously true. So it is true, but I'll explain why now. So you look at me, and I seem very tired because P is false, so I look very tired. Q is also false, though, so you don't see me with any coffee. So you see me early in the morning, I look tired, and I haven't had coffee. Then is this statement false? Well, no, technically no, because you haven't seen either part be satisfied and then false, or false then satisfied, right? So I haven't necessarily lied here. And if I haven't lied, then the statement must be true, because there are only two options, right? Remember, there's no gray area in this truth value stuff. If it's not false, then it's true. So I would consider this the technically true or vacuously true row. It's similar to the conditional, except for, remember, with a basic conditional, this one would be true as well, which is sometimes even harder to wrap your head around. Maybe this one makes more sense to you. Alright, let's keep talking about variations of conditionals. So that's the biconditional. Now let's talk about a converse. We've got converse, inverse, and contrapositive. So the converse of a conditional, and I'm going to drop P and Q here just so we don't get too confused about what's playing what role. Let's say the converse of a conditional, A implies B, is B implies A. Okay, it's just a vocab word. They're surely related because they're using the same statements, the same simple statements, A and B, but they're not the same. Remember, that's the first example I gave. It's kind of like the point of conditionals is the order is not the same. That's why this vocabulary word exists, because when you do flip them, they're a different thing. So we like to have a word for that. So if you've got some statement like, if I drink coffee, then I will not be tired, then the converse of that statement is, if I am not tired, then I must have drank a cup of coffee. Okay, now, the inverse. The inverse of some conditional, A implies B, is negation of A implies the negation of B. So the inverse, which is a new thing, it would be for this statement, let's say, for this statement right here, if I did not drink a cup of coffee, then I will not be tired, which, let's say, awake, right? Not tired is tired, sorry. If I did not drink a cup of coffee, then I am tired. That's what the inverse of this statement would be. So basically you keep them in the same order, but you negate each one. And if you have a double negative, then they cancel out. And they're not logically equivalent, they're not the same statements, they're not going to yield the same truth values. Okay. Now the last one is really interesting. It's kind of a combination of these two. It's called the contrapositive. Contrapositive. C-O-N-T-R-A, positive. The contrapositive of a conditional, you flip the order and you negate both of them. Not B implies not A. And it may be hard to tell, but A implies B is actually the same as not B implies not A. What I'm saying here is A implies B is logically equivalent to not B implies not A. And so far we still haven't defined an actual way to show this other than just kind of reasoning through it. And it might be a little complicated. Let's see if we can make sense of it. If the statement A implies B is this, if I drink a cup of coffee, then I will not be tired. So I'm telling you that statement is saying the exact same thing as, if I am tired, then I have not had a cup of coffee. Which you might hear that and say, yeah, I mean, I would tell you that that is saying the same thing. But since now you're in this class where things are maybe not as they seem, especially with these conditional statements, you might be still a little suspicious. Like, I think it's saying the same thing. Like, let me read it again. If I drink a cup of coffee, then I will not be tired. Okay. Now, the other way. If I am tired, then I have not had a cup of coffee. Again, it sounds like it's saying the same thing, right? So it seems true, but how can we absolutely prove it? How can we absolutely prove that these two are logically equivalent? Okay, so I keep skating around this idea. I'm looking at the notes right now, and in the notes I've got, I go in the order of the textbook, which I don't really like. Let me read example 1. Example 1 is asking you to write the converse, inverse, contrapositive, and biconditional variations of that statement that I give in example 1, which is, if it is raining outside, then I will have an umbrella. So all example 1 is asking you to do is say, like, for example, the contrapositive would be, if I do not have an umbrella, then it is not raining outside. It's just asking you to write different variations of that statement. I think you can figure out how to do that. Really, the only trick to that is just making sure your grammar is correct. Okay. Example 2, yeah, same thing. Except there is a negative built into that first statement. So in my hint, I said you can let P be I can find my phone, and Q be my phone is in my car, or in the car. So the original statement is not P implies Q. So let's look at that one, because that one's interesting, because the way I've done it is I've pulled that negation outside of the conditional. So I'm going to say example 2, and what I'm going to do is I'm just going to do it in symbols, and I'll let you practice writing it out with statements. So lining up the P and Q and creating actual sentences in English with it. So we're starting with not P implies Q, because we've decided to name P I can find my phone, and then we got to stick the not on it, because the whole original first statement is if I cannot find my phone, then it is in the car. Okay. And I want the converse, inverse, and contrapositive of this statement. So the converse, and remember, I'm just using symbols here. I'm not actually going to write out the English sentence. The converse, I just flip these. I don't mess with the signs, the negation, right? I just flip them. So Q implies not P. Okay. Now the inverse. The inverse. Looking at the original statement, I keep the order the same, so it should be P before Q, but I negate both of them. Now when I negate a negation, it cancels out, just like a negative in algebra. So negation of P, so that's going to be a solid P, a normal P, and then the Q gets negated. So there's the inverse of this statement. And then the contrapositive is going to be flipping and negating. Flipping and negating. So I can do this two ways. I can look at the converse and say, okay, I'm going to negate this whole thing, which would mean that would be negation of Q implies P, right? Negation of Q implies P. Or you can look at the inverse and say, I've already negated them, so now I'm just going to flip them, and you would get right back there. So the point is, it's like the contrapositive is combining these, doing this, then that, or this, then that. So if I give you a statement and straight up ask for the contrapositive, you might find it useful to do one of these first, to kind of do it in steps, especially if it's complicated and maybe there's lots of negations. Contrapositives are super useful for proving math theorems. Actually, it's a technique that math students use a lot to prove theorems, or not just students of math, but well, I suppose anyone who's studying math at any level, a contrapositive can be useful. Alright, so now that we've gotten that out of the way, on the notes I've given you a truth table for each conditional variation. That would be helpful to look at. So we see the original, of course, the P implies Q. Then we've got the converse, and look at those columns in the last column. The P implies Q is true, false, true, true, whereas Q implies P is true, true, false, true. So the truth table for P implies Q, is true, false, true, true, and then I'll just make a new column for Q implies P. Q implies P, I'm going to have, okay, reading this way, true, true, that's fine. False, true, that's fine. That's one of those vacuously true cases, right, where the first statement in the conditional is false. In fact, that would mean this one is true as well, because the Q is false here, right? But this one is true, false. That's going to be false. Since the columns are not the same, these statements are not logically equivalent. That is an excellent use of the contrapositive, actually, because here comes the definition of logically equivalent. I'm going to write it as an if-then statement. If the columns of the truth table, I gotta say what the columns are of the truth table, tables of two statements, two compound statements like this and this, are the same, then, so that's if, then the statements are logically equivalent. Now, I've pretty much already been saying this. I hadn't written it down yet. I've been implying it the whole time. If the columns of the truth tables are the same, then the statements are logically equivalent. What is the contrapositive of this definition that I've just given to you? Or not definition necessarily, but this statement I've given to you. It would be, you would flip the statements, the order of them, and you would negate both of them. So you would say, if the statements, or, yes. If the statements are not logically equivalent, then the columns of the truth tables are not the same, are not equivalent. And I've just realized that I confused myself and I wrote it down backwards. Okay, let me explain myself real quick, because I can't, if I could, I would just edit that out and redo it, but I don't have the software to do that. Okay, first of all, logically equivalent is a definition, and in math, anytime you have a definition, it's going to be phrased as an if and only if statement. It's understood to be like a biconditional statement because it's a definition. It should work in both directions. What I actually meant to write down here was, what did I mean to write down? If, I meant to write it in this order, if two statements are logically equivalent, then that means I was trying to make a point and I messed it up. Logically equivalent. Then that means their columns in their truth tables are the same. That's what I meant to write. But really, both of these statements are actually true in both directions, because it is a definition, which means it should work in both directions. But I was actually trying to make a point of this particular part of the statement, because if you write its contrapositive, which would be, what is the contrapositive of this statement? Its contrapositive would be, if their columns are not the same, I'll just kind of shorthand this, I'll just say if their columns are not the same, so not this first part, or the second part rather, not the same, then the statements are not logically equivalent. Logically equivalent. Okay, so what's going on here? I'm saying this is a legitimate statement, so take its contrapositive. Now this is saying the exact same thing as this, and we can use this to say that these two are not equivalent because their columns are different. If their columns are not the same, then they are not logically equivalent. So these are not logically equivalent. Which of course I've been saying the whole time, right? They do not say the same thing. They only do if you have a biconditional for them. Like for instance, if the statement between P and Q, if they do work in both directions and you can get a biconditional between the two of them, like a definition, like this definition, then both of the directions are true. But that's only if you have a biconditional. And in general, this is not true. Or in general, they're not logically equivalent. Okay. So, now that we know how to prove things are logically equivalent, which is just, how did we do it? We just look at their truth tables. That's all it is. Now we can do all sorts of cool stuff, like we can go ahead and prove that the contrapositive is the same as a regular conditional. So earlier I read an example with the coffee and told you that the statements are the same, and I even used it in that example of the definition of logically equivalence, that the contrapositive is the same as the original conditional. But now I'm going to officially prove it by comparing their two truth columns. Okay, so I already know this one. It's, this is a standard conditional. Okay. I don't have the negations. Maybe I should have made some columns here, but how about I just stack them on? I'll just kind of be lazy and not redraw the whole table. I'll just stack them back here. I need the negation of Q and the negation of P. Okay. So the negation of Q is just going to be this whole column, but completely flipped in its truth value. So false, true, false, true. And then not P is going to be false, false, true, true. Okay, and now I want to read the conditional of these columns. Okay, so false, false, that is true. In fact, anything that starts with false is going to be true, right? So this one is true as well. Now the true false, that is the only way to get a false out of a conditional is to have true false. And then this last column, true true, that's true. So consider these two columns. They're exactly the same. So this proves that a conditional statement is logically equivalent to its contrapositive. That does not work with the converse or the inverse, right? A conditional is not logically equivalent to its inverse or its converse. But if you put those together and make a contrapositive, then it is logically equivalent. Okay. Now we can come to some very cool applications of this idea of logical equivalence to conjunctions and disjunctions. So now we're going to abandon conditionals for a little bit and just talk about ands and ors, conjunctions and disjunctions. Consider the statement P and Q and not P or not Q. Okay, if I made a truth value of these, a truth table of these, I would need P and Q, I would need not P. In fact, I think in one of our examples from last section we had something like this, or very similar. And then I would need the P and Q, and also the not P or not Q. Alright, let's start with so with our simple statements, no negations attached, making our 4 combinations. Alright, now let's negate P just by flipping all these truth values. And then here's, oh my gosh, sorry, I was thinking of an example, something else, sorry, I was thinking of binary stuff. Because true, false can be thought of as zeros and ones. My brain was going off on a tangent about that, that's why I wrote a 0. Okay, so I've negated Q here, so false, true, good. Alright, now P and Q. So now I'm just looking at the original P and Q, remembering the rules for conjunctions. They both have to be true for the statement to be true, which means only this first one is going to yield a true, the rest of these are going to yield a false. Now what about not P or not Q? I got to remember, well, first of all I'm going to use these 2 columns with the negations of P and Q. And I got to remember that the only way an or, a disjunction, an or is false is if both pieces are false. So here I'm going to have a false. Here I'm going to have a true. Here I'm going to have a true, and here I'm going to have a true. Alright, so these 2 columns are clearly not logically equivalent, but they are complete opposites of each other. So what I want to note is that if I negate this column, won't it be exactly the same as this column? They're all exactly opposite. So if I take that whole column, P and Q, and I negate it, it is logically equivalent to not P or not Q. And I'm going to say, think of the negation as distributing. See, it's out here and it distributes to all 3 of these things going on inside, and it flips all of them. It flips the P to become negative, it flips the and to become an or, and it flips the Q to become a negation of, what did I say, the Q, right? Yeah, the Q to become a negation of Q. And this actually works in the opposite direction. If I have the negation of P or Q, that negation can distribute. It'll make the P negative, it'll flip the or to an and the Q will become negative. These 2 things are called De Morgan's laws. And if I ask you to verify De Morgan's laws, that would mean you would actually make a truth table with this and show that they are exactly the same. Which is not, it's almost what I did here, but I just didn't go that extra step to make one more column with this negated. Right, but if you wanted to, you could. That would be super easy at this point. Just stack another column here with not P and Q, and just flip all of this, say false, true, true, true. And now we can see that in fact these 2 things are logically equivalent. And that would verify this first one. If you wanted to verify the second one, you would have to make a new table because it's not exactly the same, right? You would need a new table to verify the second De Morgan's laws. Alright, consider example 3 from the notes that says, oh, I lost it, where is it? Considering the following compound statement, it is not true that Jack and Jill went up the hill. Alright, it is not true that, and then there's an and statement. So I would say if P is Jack went up the hill and Q is Jill went up the hill, then the statement would read as not P and Q. Or that's Jack going up the hill, that's Q. No, Q is Jill going up the hill. Combining them with an and then putting that it is not true in front of the whole statement. So it's important to note when your negation should be wrapped around the entire statement. And you should look for phrases like, it is not true that. Because when there's such a fancy way of saying, a negation, it's trying to imply that the negation applies to the entire statement, the entire rest of the statement. So this is what we're starting with. And then in English, we have part A is Jack did not go up the hill. So that would just be not P without parentheses. Jack did not go up the hill and Jill did not go up the hill. That's not logically equivalent to this. It's close, but do you see what it's missing? Think about this negation distributing. Doesn't that need to change to an or, right? So this is not it. Because the question is asking which ones are logically equivalent. B is, it is not true that, okay, so I know that's a big negation coming wrapped around something. It is not true that Jack and Jill did not go up the hill. How would I write that? It is not true that Jack and Jill did not go up the hill. I think it's this. Which would actually just be logically equivalent to P and Q. In other words, the negations are going to cancel each other. So this is not logically equivalent to that, so no. Okay, C is Jack went up the hill or Jill went up the hill. That's P or Q. But that's still not it. The or is there, but that's still not it. And D is Jack did not go up the hill, that's not P, or Jill did not go up the hill. There we go. That's what we're looking for to be logically equivalent to the original. Cool. So what about the negation of a conditional? So we talked about conjunctions and disjunctions for a while now. Let's get to, is there a rule for this? So we know that with De Morgan's laws, we can distribute negatives, so to speak, across ands and ors. We know how to do that now with De Morgan's laws. But is there like an equivalent set of rules for the negation of P and Q? Or the negation of P implies Q? Well, let's make a truth table and consider, P and Q and P implies Q and then the negation, and see if maybe we can look at some of our previous tables and see if any of them look close to what we get here. So let's quickly make our combinations. Alright, I already know this. You should know this by heart now. And then just to get this column, we're just going to negate all of these. Okay, so I'm seeing a lot of false. So I want something that's going to be logically equivalent to this false, true, false, false. So maybe we could look through the notes from 3.2. Did we have any that were false, true, false, false? Or if we could even get the exact opposite of that. Or no, well, no, that wouldn't be helpful. That would just be a conditional again. Let's see. Ooh, that's close. Look at this one. False, false, true, false. Not quite, though. That's this. Okay. Maybe that's something, though. That's with an and. And if you're seeing a lot of false, I would think an and would probably come into play, because an or is so nice, it lets almost everything be true, right? So I would think that an and might be involved. But that would be weird, wouldn't it, if an and came out of a negation of a conditional? So I'm looking. seeing anything. So we may, oh, nope, that's just the exact same thing we're looking at right now. So we're going to have to get creative and come up with something. So a second ago I looked at not P and Q. So let's just consider that for a second. Not P and Q. And that gave us, just looking here, it would be false, true, which would be false, and then false, false, which would be false, and then true, true. See, I'm negating P as I go along. Maybe it's a little tricky. Maybe you should draw a column that has P negated, but I'm doing it all at once here. So I'm going to read this one as true, false, and that would be false. So that's very close to this. It's just these are mixed up. So how about I try P and not Q? So now I'll read this as true, false, which is false. True, true, which is true, looking good. False, false, which is false, and then false, true, which is, false, true, which is false. There it is. So this P and not Q is equivalent to the negation of P implies Q. So we had to go dig into conjunctions to get a negation of a conditional. So the conclusion here is that the negation of an implication is logically equivalent to this conjunction with P and not Q. And the way you would read this is, it is not true that P implies Q. That's how you would read this part here. So as an example with like the coffee, going back to if it was, if I drink, what was it? If I drink a cup of coffee, then I will not be tired. I could say, it is not true that if I drink a cup of coffee, then I will not be tired. And somehow, that statement, what I just said, which is like such a mess, like who talks that way, but we can show with symbols that that statement is logically equivalent to me saying, if I drink a cup of coffee and, or not if, sorry, nope, threw an if in there, not supposed to be an if. It's logically equivalent to this statement. I drank a cup of coffee and I am tired. Because the Q is I am not tired, right? So I gotta negate that. So saying these with an example in English is like, it gets too much, right? You would have to write it down and like really think about like, okay, is this actually saying the exact same thing? So it just shows how helpful these symbols really are. Because if you can get the statement in symbols, then it takes, as long as you know your truth table stuff, it takes a matter of seconds to say, oh yeah, they are logically equivalent. Even though if you were going to sit down and explain to someone with an example that the statements are logically equivalent, you'd be there for a while. You'd probably confuse yourself, right, trying to show it. But with a table of truth values, there it is. I mean, it took me less than a minute to draw this table. Example 4, just an example of negating an if-then statement. It's, if I go to the diner, then I will order pancakes. So I'm going to actually write it in English now. And what I want to do is I want to negate this and then give you a logical equivalence to its negation. So I know I'm going to use this little idea that we just wrote down. But I'm not going to do it in symbols. I'm going to do it in words for you. So right now, what I've written down, this statement in words, is this if P then Q. So I want to say the negation of it, which if I read it on this side would be, it is not true that if I go to the diner, then I will order pancakes. But I want to write a logically equivalent statement that doesn't have that if-then. So maybe a simpler way of saying it, which that's relative. But anyway, so P is I will go to the diner, or I went to the diner. Well, let's say I will go to the diner. Let's try to keep it grammatically correct. And, here comes the and then not Q. So I will not order pancakes. So the negation of this English statement here, the negation of it, trying to say the opposite of this statement, is the same as saying this. So if I'm trying to tell you, think about, let's see if we can reason through this in our minds without using symbols. We've already proven it with symbols, right? But let's see if this makes sense to us. If I go to the diner, then I will order pancakes. That makes sense to me. So you're saying, like, if we go up to Waffle House, then I'm going to order pancakes. But I want to say the opposite of that. I want to say it is not true that if I go to the diner, then I will order pancakes. And I say that out loud, and everyone's confused, so I say, okay, let me give you, like, instead of me saying it is not true that if we go to the diner, then I will order pancakes, I'll give you a different way of saying that. What I want to say is, I will go to the diner, I will go to the diner, and I will not order pancakes. I think that is simpler to understand than putting a negation at the back of a, or at the front, rather, at the front of a conditional. Okay. Example 5 is to write the negation just using symbols, thank goodness. Don't have to think too hard. That's kind of the point, is you don't have to think too hard if you can get these things in symbol form. What is it? A implies C and D. And I want to negate it. So I'm going to have to do a little bit of substitution in my mind. Think about what's playing the role of what here. So consider the rule. It's the negation of a conditional. Okay, I have the negation of a conditional where the P is playing the role of A. So P just comes right over, which is A. Then my and then not. And what's playing the role of Q here? It's this whole statement, C and D, in parentheses. But the whole point of writing a statement out with logical equivalence and distributing these negatives is so that you don't have any negation of like compound statements like this. You want your negations to be directly attached to the simple statements, because it's hard to understand, statements when you have negations attached to the entire statement, like when it's wrapped in parentheses. So we can actually do something with this, though, can't we? Because we know how to distribute negations across a conjunction. So we'll say A and, that part doesn't change. And then here, the negation of C or the negation of D. Now, I do want to say that when you're writing these statements, in this way, we did distribute across the parentheses, but it's still implied that this statement should come first, so you would still want to have parentheses around that, just to show that this statement comes first, then the A and. Okay. Cool. But it wouldn't really matter actually anyways, because we know that the ands and ors, they're able to commute, right? So we could just drop the parentheses technically. Now within a conditional, parentheses, just if you have parentheses telling you orders, then parentheses definitely matter there, but there's no conditionals here. But it's still kind of better form to keep this wrapped in parentheses, because it was implied back here, well really all the way back here, that this statement comes first. And the parentheses were absolutely necessary here because of that conditional. So anything that implies order to a statement with parentheses, probably keep them there. It's just better form. Even if, if you're distributing to kind of get rid of this negative out here, or this negation out here, distribute it, but still wrap the C and the D and its new operation in between them, its new logical operator, whatever you want to call it, this little disjunction symbol, wrap the whole thing in parentheses. Alright, that is the end of 3.3. Got some exercise problems there for you to look at in the textbook. And that is it.